So this is the outline of this presentation. I will first present my research activities and the facilities we have developed to support these research activities. I will present you the context of this lecture, and then I will show you the Guadeloupe grid model we have developed in real time for this problem. And I will finish my lecture with some PHI application we have used with this Guadeloupe grid real-time model. Okay, so as I said at the beginning, I'm part of the L2EP laboratory, which is an electrical engineering science devoted laboratory. It is divided into 5 teams and headed by Professor Francis Perriou. So you have modeling for electrical machine, control for electromechanical system, design optimization for electrical machine, power electronic team, and my team, the power system team, which is headed by Professor Benoît Robins. So this team is, in this team you have 5 professor, assistant professor, 14 PhD students, and 1 research engineer. And we work on the development of methodology for the supervision of distributed generators, such as renewable energy. We work on in the integration of this kind of generation in power system. We work on microgrid too. We study the insertion of storage system in the electrical grid. And we work on the integration of renewable energy in the market, in the electrical market. So to support all these research activities, we have developed what we call the distributed energy facility, which is an experimental grid on which you can connect any kind of equipment. So you have emulators like industrial process, emulators of renewable sources, emulators of classical production. We have a supervision software which can control each equipment. We have real devices. And we have also a real-time simulator. So to illustrate that facilities, just show you some equipment we have here. So we have an emulator of classical production, which is an old synchronous machine driven by a DC machine. And you have the possibility to emulate a group control for the frequency. We have also a photovoltaic power plant, which is 18 kilowatt peaks, and you have the possibility to connect this power plant to our experimental grid. We have also storage device, which is only now a supercapacitor device, but we will be soon have some battery device and hydropneumatics storage device, which will be developed in a research project. We have also power amplifier, but I think you will have a presentation by Puissance Plus this morning which deal with this kind of equipment. We have also our SCADA software, which is PCVu, which is developed by Arc Informatique. So it can interact with all our equipment by using OPC protocol or Modbus TCP/IP, and soon by using EIC 61850 communication protocol, which is devoted to electrical grid control system. So the most important equipment is here our real-time simulator. In fact, we have 2 targets which can be totally independent. We can use the Firewire link to connect each target together and to increase their power calculation. So here, by using this simulator and our power amplifier, we can do what we call power hardware in the loop, which is illustrated by this slide. In fact, you can connect a virtual embedded device with a real device by using this kind of amplifier. So you can, for example, connect our photovoltaic power plant to a virtual network which is simulated in real time on our real-time simulator. So you can see the impact of the photovoltaic power plant on the network, and you can see the impact of the network to the real device. Okay, this is what we call the power hardware in the loop. Okay, so now I'll start with the context of this lecture. So we are on island grid. So it is a weak grid. You have only one grid operator. You have a lot of fossil fuel power plants. And you have more and more integration of renewable energy because, for example, in Ireland you have a lot of sun. So it is you have more and more photovoltaic power plant inside this kind of network. So as you have more and more renewable energy, the power system inertia decreases, and you have a problem of primary reserve allocation. So the effect is that the fossil fuel power plant are used on a non-optimal point, and the pollution increases a lot. So one solution is to use what we call DESS, distributed energy storage device, and connect them to this kind of island grid. So to illustrate the problem inside this kind of electrical grid, here you have a curve which was measured on the Guadeloupe grid after a fault of a power plant. So as you can see, you start with a normal frequency, then you have a fault from the power plant, and you have a peak frequency here, and you are below 48.5 Hertz, so you start to cut off some customer. So the main goal of this project was to test using PHI applications the advantage to connect some storage device inside this kind of island grid. So we used our supercapacitor storage device to see if it can support this kind of fault. And the application case was to use the medium voltage network of the Guadeloupe island. So here you have the presentation of this network. So what we want to simulate, to model, is the network which is in red here, which is 63 kilovolts. You have a lot of fossil fuel power plants. You have diesel power plant, combustion turbines, coal-fired power plant, geothermal, some wind turbine, and some photovoltaic power plant. Okay, so here the first thing to do is to obtain the real-time simulation. So we need to have a reference to obtain. And EDF allows us to access the Eurostag model they have developed. So Eurostag is a classical software used to, like EMTP, if somebody knows. It's a classical software to used to simulate a large-scale power system. So this was the reference result we want to obtain. So the first step was to make the simple system model and to obtain the same results than the Eurostag model, because RTLab used simple system toolbox to simulate electrical system. So the step 2 was to compile this model and test it in real time. And then we start to insert the storage device and make some comparison with pure simulation result obtained also in real time. Okay, so here is the comparison between the simple system simulation and the simulation from Eurostag. So here you have a fault from a coal power plant at 20 seconds. So here you have the frequency response. In red you have the frequency response in simple system, and in blue from Eurostag. And here you have the power generation response from another power plant. And you see it's approximately the same results. The main difficulty to do that is that you have a lot of parameters from the generator, and somebody knows that perhaps. Eurostag and simpler system doesn't use the same, for example, per unit system for the synchronous machine. So the main difficulty was to transfer the parameter from Eurostag to a simpler system. So you have a lot of work behind this before obtaining this kind of results. But you can have the same results in simpler system than in Eurostag. Okay, so here is the real-time model we have obtained this is a real-time simulation of the Guadeloupe grid. So we wanted to test it inside our target, but it was too huge to be embedded into only one core. So we used what is called a stub line in the RTLab, in the Artemis toolbox, to separate this model into several cores. So we use a total of 4 cores to simulate this kind of network. Okay, so here is the results we have obtained from the real-time simulation. So in blue you have the Eurostag response, frequency response. In green, the simpler system response. And in red, the real-time response obtained from our RTLab simulator. So we have obtained good results. What we can conclude is that stub line introduces a small lag. You have a small difference between the real-time results and the simpler system results. But it was good enough for us. We wanted, we can deal with that. Okay, so now we can start to insert our storage device. So the scenario was, we have a fault of the coal power plant, which was producing approximately 23 megawatts for a total consumption of 140 megawatts. And we want to insert a storage device here in the Sainte-Anne substation. And the objective was to reduce the peak frequency and dynamic transient settling time. So we want to reduce this peak frequency here and to have a settling time, reducing time. Okay, so this is what we have done. We have to test this kind of insertion of storage device. We have done some PHIL application. So we measured here the voltage in Sainte-Anne substation, and we connect our real device through our power amplifier, and we re-inject the current inside the Sainte-Anne substation. So this is another application of PHIL application, which I have presented at the beginning. Okay, so here is the result we have obtained. The goal was not to reach the yellow line here, not to cut off a customer. So in red here you have the frequency measured in simulation, in pure simulation, and in blue this is the frequency measured in a PHIL application. So as you can see, you have you have small error between the two results, but we have done some improvement for this kind of application, and the results now is approximately the same. You have a small lag because you have some conversion. You use digital to analog converter or analog digital converter, and which introduce some delay between the conversion done in PHIL application. So here is some picture of the storage device we have used. So here you have the supercapacitor modules, which each module can reach 48 volts and 160 farads. Here you have a box which contains the power converter and the controller used to control this converter.